Brian Williams. He'll just take a minute to set up and then we're ready to go.
Turn up the volume. Oh, I guess he turned up the volume. Hi. Thanks to the organizers for inviting me. I don't really consider myself a pseudorandomnessist by nature, but I have something. It's unpublished, but I told Luca and Omer and other people about it, and they said they didn't know how to prove it, so I'm going to tell you how to do it. And what's really nice is that because this is at the beginning of the workshop, if you have any ideas about what else to do with this, there's a lot of time to do it. So this is about approximate counting for systems of quadratic equations. Okay. So the problem we're going to look at is MQS. So you're given some polynomials, P1 through PS. Okay, they're F2 polynomials in variables. Okay, and well, usually you just want to know is there some satisfying assignment to all of them. So you want to know. I'll usually just drop the vector notation, just talk about x. So you want to know, do I have an x that satisfies all these? So this is NP hard, NP complete, in fact. We're going to look at the counting problem, for which exact counting, these are quadratic. It's important that these are degree 2 polynomials. Well, already for degree 2, it's NP hard. Counting the number of solutions is a sharp P hard. We're going to look at an approximate version of this. So call it approximate in QS. And now we're given these things. We're given a parameter epsilon. And we want to know a value that approximates the fraction of satisfying assignments. So I'll just write it out here. So if you take V minus the probability of a random assignment that all these equations are true, the difference is most epsilon. Okay, so we want to get an additive approximation to the fraction of satisfying assignments. Okay, now random sampling can do this. Right? You can do it very efficiently. And let's say, so I've got like S equations and variables, poly n over epsilon squared time. Okay, so just take order 1 over epsilon squared, random samples, compute the fraction from that, you're good. Okay, so that's easy. So the theorem here is that you can get a completely deterministic algorithm with exactly the same running time. Well, exactly, if you allow me polynomials. So the theorem is that there exists a deterministic that time algorithm for this approximation problem. So that's the theorem I want to talk about. And there are some, so the field being 2 doesn't seem to matter so much. It makes the presentation a lot easier. You have less of a headache. The degree 2 part that seems trickier to generalize. Generalizing to finite fields does not seem so tricky to do. Okay, so let me say a bit about the prior work. So just to put this in context, the interesting thing here is that the dependence on epsilon is just 1 over epsilon squared. Okay, so just this is the best prior work I know of. Perhaps you know some more, and I'd be delighted to hear about it. So Trevisan showed that for approximating the solutions to a D CNF, so think of this is so it's an N of ors, and each or has at most D variables negated or not in it. Okay, so this is, you can think of this as a very special case of, say, degree 2 polynomials over, or degree D polynomials over F2. Okay. And so there he gets a polynomial time algorithm, so let S be like the size of it. And he gets an algorithm which has dependence epsilon to the C, D times 2 to the D, for some constant C, at least 1. Okay? So the dependence here is pretty bad, even for D equals 2. Okay? So over there we get actually epsilon squared. So, and so his is white box in the sense that it has to look at the CNF to get the right answer. And mine is also white box in the sense that it has to look at the system and determine what to do. There are some black box things. The best known to my knowledge is that of Viola, who gives a sort of pseudorandom generator for fooling degree D polynomials. And this gives you a degree D approximation for degree D F2 polynomials, for example, that runs in order n to the D. Well, I mean, degree D polynomial could be that big, times 1 over epsilon, another C times D times 2 to the D. Okay. So again, these dependencies are not so great. One thing I want to mention, which will be useful for us, is that, so this is from Aaron Kropinski from 1990, that if you wanted to exactly count the number of solutions to a single polynomial of degree 2, then you can actually do that. So degree 2 F2 polynomial, if you want to count exactly, you can do that in order n cubed time. It's mainly, the idea is mainly finding some nice basis change for the variables so you get like some very nice numeral form, in which case the number of satisfying assignments is easy to compute. I mean, I won't say any more than that, but this has been generalized to finite fields. So for any finite field, you can get some polynomial in time algorithm for counting the number of solutions to a single degree 2 polynomial exactly. Okay, this was by Woods. All right, so what's the idea here?
So the dependence on Q, is it like, if Q is huge, like exponential?
I'm not sure. I think it might be exponential in Q. I'm not exactly sure. Have to look. Yeah. So the first idea, we don't have to do this, I just want to say, but it makes the rest of the acquisition pretty easy to think about. The first idea is we want to count solutions to sort of the complement. So we want to count solutions to P1 of x1 or P1 S x1. So we want to find solutions that make at least one of these equations 1, okay, over F2. All right? So to that end, let S sub I be the set of those points that make the ith polynomial 1. Okay, so what we want is to approximate the cardinality of the union of these different sets. Okay, so to do that, I'm going to make a definition. There's probably another name for it, but I really like my name. So we're going to look at an operator on a collection of sets. So let A1 through AM be some collection of sets. And we say that this sort of O plus, I guess, in LaTeX of the different A sub i's is a set of X. So X occurs in the odd number of the A sub i's. Okay, I call this the odder section. Okay, I don't know. Okay, fine. Do you know, is there actually a standard name for this thing?
For two sets, it's symmetric difference.
For two? Yeah. Yeah, odder section, okay. And then I call this sort of thing the oddity. Okay. Right. All right, so the idea is that you're going to represent this cardinality of the union that we want as some linear combination of a small number of oddities, of, say, subcollections, of deterministically chosen subcollections. So there's going to be some poly S over epsilon squared things we're going to sum up, and there'll be some coefficients, say C sub k's, or the k different things here, and there are going to be some S sub ij, something, different things from the subcollection. And the point is that each of these oddities can be counted in polynomial time. Okay. Well, why is that? Well, it's pretty easy to see that if I did this, if I took the oddity of some subsets of this, right, then that's just a set of X such that the sum over the same J's, the same Pj sub Ix, so let me write it like, so I'll just index these, just some arbitrary subcollection of the polynomials. I'm just looking at the number of solutions that make this particular equation over F2 true. Okay? So the idea is I want to approximate this union with a fraction of assignments in this union up to some epsilon. I will exactly count oddities. So in other words, I will just take some deterministically chosen linear combination of the polynomials in my system. I will count the number of solutions to each one. Okay? And then I'll take a linear combination of that. And that will be an additive approximation.
And then this is, so what you're looking for is a sparse probabilistic polynomial for or?
Approximating polynomial. Yeah. I want a non-probabilistic polynomial.
Yeah.
Yeah. I want a deterministic. Yeah. So it actually will prove something a bit stronger along the way. I mean, what this representation is saying is that actually, just say it off here to the side, if you've got a epsilon approximation, so you're approximating the fraction within additive epsilon to the number of solutions to, say, S degree D polynomials, again, over F2, we can always reduce this to making our epsilon, say, slightly smaller, epsilon cubed over S squared approximation, the number of solutions to 1 degree D polynomial. So that's nice. I mean, it's a general reduction. I mean, it would work. So in other words, independent of the degree D, what I'm saying is going to work. So systems seem much harder to count solutions to than a single one, especially in this case. So it's nice. And I hope there's more to say in this direction. Any questions so far? All right. So let me tell you how you.
Sorry, these are two different results. So it's the same.
Infinite.
That theorem is the reformulation of the same result, or it's a different result?
I mean, it's basically saying if you have this representation, this theorem follows. Yeah. Like it will follow because this polynomial in S is actually S squared. And so like having this kind of approximation means I get sort of epsilon times 1 over this total number. So getting an approximation to each of them, which is really that tight, will give us epsilon approximation to the whole thing. Yep.
Do you have a bound on the sum of the absolute value of CKs?
Yeah, each CK is actually very easy. It's like 1 over 2 this number.
Will this imply like what I'm wondering is, will this imply a PRG? Like if,
let me tell you how it works, and then you can tell me. Yeah. So we'll use. Oops. Maybe I should use a different pen. No. We'll use epsilon-biased sets. So what are these things? These are really wonderful objects constructed by Noor first in 1990. So take some subset of f to the n. It's epsilon biased if for all x in f to the n, this thing will closely approximate the parity of, say, a random inner product on x. So suppose I've got a uniform random r in f to the n, and I'm looking at the probability that this thing is 0. Well, that's going to be within epsilon of the probability over this epsilon bias set of the same thing. Okay? So this is, so you can think of this epsilon bias set as sort of the output of a pseudorandom generator that's fooling degree 1 polynomials. So linear functions over f2. And so this is all like mod 2 stuff. Okay. And what we'll want to use is the fact that these can be very efficiently constructed. So for example, a theorem of Alon, Goldreich, Hofstad, Peralta from 92 says that in fact we can get in polynomial n over epsilon squared time algorithm that will construct, so we construct an epsilon biased S. And the cardinality of this S is, say, most n squared over epsilon squared. Now, if you were to pick a random collection of S, you can get away with n over epsilon squared. Tiny bit better depending on how the error epsilon and n depend on each other. But this is the best known explicit construction for what we want to do. What we want to do is have 1 over epsilon squared error. There are better constructions if you allow epsilon cubed, you can make this thing. And there's other things, other trade-offs like that as well. But for us, right, we care about getting this optimal sort of epsilon. Basically matching random sampling. Okay, and so the main lemma here is, suppose I've got some set, R1 through Rm. It's a subset of f to the t. And let's suppose it's epsilon over 2 biased. Okay. And also let A1 through AT be arbitrary subsets of some finite set U. Okay. Then I can approximate the union of these things in the following way. If I take 1 over 2m times the sum from I ranging from 1 to m of various oddities, which are determined completely by these vectors here. So the point is, for every single vector here, I will look at the coordinates that are indexed 1, right? It's their t coordinates, and I will just compute the oddity of the subsets that are 1 there. So I'm going to say j such that r sub I j equals 1, a sub j. Okay? So if I take these two things, this thing is actually less than epsilon. So this is exactly the quantity I'm going to use to approximate this thing. Yep?
Presumably you mean less than epsilon times 2 to the n.
Sorry?
Presumably you mean less than epsilon times 2 to the n.
Oh, sorry. In fact, I mean less than epsilon times the size of the universe. Thanks. Yeah, I guess I'm like mentally dividing through by the universe. That's right. Thanks. Okay. And this lemma follows from the fact that the OR function actually has a sparse representation in the Fourier domain. I guess I could do it here. I don't have a whole lot of time left, so I will just say what claim it follows from. And it's not so hard to think about how this kind of approximate formula follows. So it follows from this, the claim that for all inputs, say x on t bits, this is due to the earliest reference I can find is the Lawn and Brook from '94. The OR function on those t bits is very closely approximated by 1 over 2m, some of these i's, and then I compute for each of these i's is j, r at j equals 1, x of j mod 2. So this function here, you should think of it as taking an integer, okay, and outputting a 0, 1 value. So it takes this integer sum, computes mod 2, renders that as an integer, 0, 1 integer, and sends that out. Now you're computing this sum, okay? It's over m things. Okay, and I'm using this 2 over m to kind of average out what's going on, okay? The idea is that if the vector is all zeros, the OR should be 0, right? All these sums mod 2 are going to be 0 if all the bits are 0. Okay? So it's 0 minus 0, and it works perfectly then. Okay? All right? Now, suppose there's a bit that's set to 1 here. Okay? Then, if I chose a random, so if there's a bit in here set to 1, if I chose a random vector and took an inner product with it, it's probably half of being 0, exactly 1/2. Okay? With epsilon biased, I'm off by epsilon from half. All right? So this quantity here, the sum, is going to be between m over 2 minus epsilon m over 2 because I'm using whatever epsilon over 2 biased in my set, and m over 2 plus epsilon m over 2. All right, I'm dividing by 2 over m, so this is actually 1 minus epsilon, 1 plus epsilon. Okay? So when the OR is 1, this is actually approximating it to with an epsilon as well. Okay? And the way you would get this lemma from the claim is just imagine rewriting what the union means. The union means the OR of some indicator variables on all of the elements here. So it's like you sum over all of the elements in the union, and you take the OR for every single set, whether that element is in that set or not. Okay? And so you can write the union as just a sum of like OR functions being applied. All right? So then you would, using this lemma, say, oh, well, that's actually equal to the sum over all the elements of this thing being applied. You basically exchange the sums until the sum over all elements is within here. And when the sum of all elements within here, this is actually computing exactly these oddity things. All right? So I think that's kind of all I want to say about these lemmas and claims. I hope it's somewhat clear. Let me sort of tell you what the algorithm is now. Okay. Sort of the final algorithm after this dust is clearing. So you're given an MQS instance. So these P1 through PS, each in n variables. So think of this as a vector of n-bit variables. And so the first thing you do is you build these epsilon over 2 biased sets, but it's over f2 to the s, okay, the number of the polynomials. Okay? And then this epsilon biased set will have a bunch of vectors in it, not too many, but these vectors will determine which of these sort of subsets of polynomials you will sum together and count their solutions to. So then you'll count the number of solutions to size of s. So this is some size of s, degree 2 polynomials. each of which is determined by some subset, basically some mod 2 of some of these. Okay. And then, so this will give us an estimate, say W of the union. And then we're just going to output 1 minus that estimate. Right, because we're actually getting the union of the, so, yep.
Sorry, I'm confused. Is it the size of S many degree 2 polynomials or the number of elements in the epsilon-biased set many?
This is the number of elements in the epsilon-biased set. The set is S.
The set is over.
Oh, sorry. You're getting confused about notation? So the S of I means the set of solutions to this polynomial, the set of points that make this polynomial 1. And then T is a set of vectors in S bits. And so each of those vectors will determine some subset of those polynomials to sum together mod 2, and then you count the number of solutions to those things, to each of those things. And so the point is, this thing is right, order S squared over epsilon squared by what we have here. Okay? And each of these estimates, so each of these counts will take us order n cubed time, okay, by the fact that for a single polynomial we can compute that. And so we get polynomial in n and s divided by epsilon squared. But note that, so we had this little trick where we were wanting the number of solutions to this, we just looked at the complement, so then we started working with or. You could get a polynomial for n directly if you wanted, but it's a lot messier to write down. There's like some minus ones and like other weird sums you have to carry around. So this sort of makes it a bit cleaner. I have like 1 minute left. I have some remarks, I guess. So in retrospect, what's going on is kind of similar to Lineal and Nissan. So they had some work on approximate inclusion-exclusion, where they showed that the union of a family of sets, so the cardinality union of a family of sets, can be well approximated by sums of small intersections, so up to like square root of the number of sets. Okay? And the way they did this is they just applied the fact that over the reals, you can get approximating polynomials due to Nissan and Segedi for the OR function. Okay? So this is kind of taking that, but getting a different representation. Instead of intersections, XORs. But here it's really nice because XORs of F2 polynomials are just F2 polynomials. I think it works for finite fields, but it's a longer talk. Let's see. Yeah, we can talk later if you have ideas about it. Thanks.
Thank you very much. I do think we have time for 1 or 2 quick questions.
So Ryan, what about higher degrees?
Sorry, what?
Higher degrees?
Oh yeah, so it would suffice to say for degree 3 to have an approximate number of solutions to a degree 3 thing. Actually, you can just take what Viola has, so this thing here, okay? And if you want to say epsilon prime approximation, you would just plug in, say this quantity for this epsilon, and you get something there. So I can write out what it is, but you can also just take this and plug it in and see. It's like S over epsilon to the order d times 2 to the d for like any degree, any system of degree d polynomials. Yeah.
I mean, I think if you're just plugging in a pseudorandom generator, then you can just use the same epsilon.
The same epsilon.
Yeah, you don't need to change your value of epsilon.
Well, if you want to apply what I just said.
Well, but I'm
need to,
saying,
but-
but when you're just doing a pseudorandom generator, there's no reason to do this different decomposition if you just do sort of the average of the
Oh, I see.
things over all sets. Then
I see.
some of the coefficients is 1.
I see. I mean, I guess the point is to end up with an epsilon approximation at the end. I need a close approximation here because I'm summing 1 over this many times epsilon stuff here, and I want them to, like, I don't want the error to accumulate.
Some of the sizes of the coefficients.
Some of the sizes of the question. Yeah, I mean,
So can't you reduce the higher degree case to the to the degree 2 case, but since you're looking at systems of polynomials,
Yeah,
you just introduce new variables
you can.
to be quadratic functions.
Yeah, that messes up your fraction though, right?
Messes up
Because
the
you start out with 2 to the n total assignments, now you get 2 to the n.
Right, no,
Yeah, it'd be
sorry,
really
not
nice
the
if I could just like
if it was
apply
like
NP hardness
approximating the
reductions.
number, right.
Yeah, if I were, if it were a different
Yeah,
approximation
multiplicative
problem.
approximation, that would work. but
Yeah,
not
for
right.
additive approximation, it totally destroys it because
Yeah.
your epsilon times 2 to the n, like stuff getting stuck in there. Yeah.
Great. We'll reconvene at 11. There's coffee outside. Let's thank Ryan again.